All right, this video will go through how to do the disk method for finding volume. What we're going to be doing is building off the lesson we did for finding area between two curves. But instead of just finding an area, what we're going to do is we're going to rotate that area around some axis of revolution, usually the x-axis, but we could use other lines as well. And what's going to happen is we're going to generate some kind of three-dimensional solid. So it's a little hard to picture, but if you can imagine rotating this thing around, you would end up with like a donut shape, right? If you rotate it all the way back to 3D, to 360 rather. Or, in the case of like this picture down here, if we took this region and rotated it around, we would end up with this solid. And we can calculate the volume of that solid using the technique that we're about to derive. Okay, so to do this, we're going to go back to the idea of finding area by using approximating rectangles, right? Like when we did Riemann sums. But rather than look at all of the rectangles, we're just going to look at one of them and think about what happens. So let's just say, this blue region, I would like to rotate it to get this solid that's pictured over here. Well, okay, if I rotate this rectangle, you can imagine it like coming down here, going 360 degrees all the way around, right? What that would do is it would trace out a cylinder or a disk. That's why we call this the disk method. And we can figure out the volume of a cylinder because we know that formula, right? The formula for a cylinder is pi r squared h. Either you learn that in geometry or in this course or wherever, but so let's see, we need to figure out the radius of this cylinder. Well, where did it come from? It came from rotating this rectangle. The radius of the cylinder is the height of the rectangle. And okay, well, how do we figure that out? Well, the height of the rectangle is given to us by the function that it is on. So let's just call this f of x. Okay, so the radius is f of x. The height of the cylinder is whatever change in x we decide to use. That's the width of the rectangle. And ideally, we would like to make this go as small as possible, right? We'd like to really ideally get it to 0, get an infinite number of cylinders. And that's that idea, we've talked about this, right? When delta x gets infinitely small, we approach dx, right? This infinitely small change in x. And we therefore get this integral. Okay, and sometimes we pull the pi to the front because we can pull the constant out, and we integrate from the bounds of the region, so from A to B. Okay, and this will calculate the volume of this solid. Okay, we can build off of this. Okay, so this would be for just rotating a area between a function and the x-axis, but we can build off of this to rotate between any two functions. If we're trying to find the area between them and rotate that around, again, to get some kind of like donut shape. All right, so again, we'll think about some representative rectangles. Let's just say that, our functions look like this, and we're trying to find, this region rotated around. Well, think about one rectangle rotating around, right? And if you imagine sort of the rectangle coming out of the screen at you, rotating back through 360, all the way back around, it would generate this shape, this donut shape, or we call it a washer. Right? If you've ever like put something together, those little metal rings, that's why we call this the washer method sometimes. Well, a washer or a ring or a donut is really just a big cylinder with a little cylinder taken out of the middle. Okay, so what we can do is we can think about, in geometry, we would say this right? If r, big R, is the radius of the big cylinder and little r is the radius of the little cylinder, then we could do pi times big R squared h minus pi times little r squared h. Well, so now let's just take that to calculus. So, okay, we'll do, if r is the radius of the big function, so let's just call this r of x now. Right, we can do this minus the integral pi of little r. And again, whatever region we're on, let's just say from A to B or something, we would integrate from A to B. We could make this easier by combining the integrals and factoring the pi to the front. Okay, so usually we're going to write it like this. And sometimes, you can put parentheses here if you want. And technically we need them there too. All right, and that calculates the area of the region created by revolving that region around the x-axis. All right, so we'll do some examples to show how to set this up. And most of the time you are just going to set this up. Okay, often the instructions given to you will be something like this: set up but do not evaluate. In other words, we don't actually need to get the final numerical answer, because usually we would just use a computer to do that anyway, or a calculator. So that's not really testing anything. It's just an extra step that's just tedious, right? So anyway, they give us a picture here and they tell us that f is x squared plus 1. So obviously that is the parabola, and the line, right, x plus 1. And they want the region bounded by those things. So we know that'd be like right here. Right, and they want the volume of the solid generated by revolving about the x-axis. Right, so the x-axis is here. So let's see. So I would do the integral from a to b, r squared minus r squared, big R squared minus little r squared. Okay, so my a and my b in this case. Right, so we need to find our bounds. Well, obviously this is 0. And, you can just think about it, or you can set these things equal and solve if you want, or, but ultimately you're going to find that this is 1 if you just think about it in your head or whatever you do. All right, now when we say big R, what we mean is like the outer radius. So in other words, as we rotate around, right, this line is going to be the furthest away from the axis, so that is going to make the outer part of the cylinder. Okay, so we'll say x plus 1 squared minus, and then the inner radius would be the parabola. And that's it. We do not need to go any further than that. You do not need to simplify. Okay, unless they explicitly ask you to. To go about the y-axis, well now we're going to rotate this way. And to do that, now I need to draw my rectangles in this direction. Okay, which means we need to go back to that idea of integrating with respect to y. So what I'm going to do is I'm going to rewrite my functions in terms of, in terms of y rather. So x would be y minus 1. And then here, x would be the square root of y minus 1. Really plus or minus, but we only care about the positive branch, right? So we'll just leave it like that. We need to think about our bounds. Okay, this is 1 right here. And this is 2 right here. Okay, again, you either plug in to figure it out or use your calculator or whatever you would do. Okay, so we're going to integrate from 1 to 2. Now, careful, the outer radius and the inner radius are going to switch this time. If we rotate in this direction, right, think about it, this is going to be further away from the axis of rotation. So now the parabola becomes my outer function, or outer radius rather. Right, and that's my setup. To go one step further with this, let's take the same region and consider rotating it around a different line that's not the x or the y axis. So in this case, y equals 3. Okay, so 3 is up here. We know it's definitely above because we just found that region, right, stopped at 2. Okay, so now we want to rotate around here. And so the way to think about this is, this would end up like there'd be some gap here. This would be like here-ish. You would get like a donut shape, but around this line instead of around this line. Well, why don't we make our problem easier by shifting everything down so that it lines up with the x-axis? Okay, in other words, instead of rotating around 3, let's shift everything down by 3 units so that my axis of rotation lines up with the x-axis. Because if I do that, then I can just use this formula I've already derived. Okay, so how do I take something and shift it down by 3 units? Well, we know from pre-calc, right? Just take away 3. If I do x squared plus 1 minus 3, that has the effect of shifting that parabola down, right? It becomes x squared minus 2, so it shifts down by 3 units. Okay, so this is the idea. We're going to take our functions and move everything down. Now, when I do that, right now I'm still rotating this way. Okay, this is my outer radius. Okay, so we're going to integrate pi. It's always pi, and that just comes from, again, the formula for a cylinder. We're drawing rectangles this way, so we're going to use x values. So from 0 to 1, the outer radius is the parabola, but shifted down by 3 units. And the inner radius is the line, but again, shifted down by 3 units. Now you could leave it like that, of course, if you want to clean that up a bit, that would be okay. But you don't even have to. And that would be your answer. Either way, I would accept either answer. Right, so the idea is, if you rotate around this line, you're going to get the same solid as if you had rotated around this line. It's the same donut, just shifted down by 3 units. Hopefully that makes sense. Okay, I'll go through one more example. And this actually comes right from an AP test, by the way. R is the region bounded by the graphs of natural log and x minus 2. Okay, now this will not be as nice, and we'll ultimately need a calculator to do this. But we can think about setting this up even if we don't know our bounds, and then we'll go and find our bounds. All right, for right now, let's just call them A and B. Find the area of R. Okay, so this is going back to top minus bottom. All right, so in this case, the top function would be the natural log, and the bottom function would be x minus 2. Okay, if we were just interested in setting up the integral, this would be our setup. We would just need to go find our bounds, which we'll do in a minute. All right, to do that, easiest thing, honestly, use Desmos. That's what I would do. ln x minus 2. Right, and then, boom, boom, there you go. There's your bounds. No work required. No, fiddling around with second trace or any of that. So let's remember those numbers, 0.159 and 3.146. 0.159 and 3.146. Okay, let's actually write those down so we don't lose them. All right, we would type that in our calculator, get an answer. I'm more concerned with the setup than the final solution. All right, and now we have this New idea. So how would I find the solid generated by rotating around the line y equals -3? All right, so first of all, we need to think, is like in the region, is it below the region? So this is, again, where a graph can be helpful, but we see that this goes as low as -1.8, so certainly -3 would be below that. Okay, so, adding that to the picture might be helpful. So again, let's shift everything up by 3 units so that my axis of rotation just lines up with the x-axis, and that makes everything easier. Okay, so now we're going to use pi because we're getting a volume. We're going to use the same bounds. Okay, it didn't shift left or right, it just shifted up and down. And then we're going to take our function. Now, careful, if we're rotating this way, let's just make sure which one's the outer function. Well, okay, the ln will still be the outer function because that's going to go the further distance around. But we're going to shift it up by 3. That's all. Okay, and then we're going to take our line, and same thing, we're going to shift it up by 3 units. All right, and if we wanted to get the answer, let the calculator do that for you. All right, one final example with this. So here they say write but do not evaluate. Okay, they don't even care about getting the answer. They just want you to set up the integral. The expression that would be used to find the volume generated by going about the y-axis. Okay, so now going this way, and again, drawing our rectangles this way. So that means I need to get my inverses, right? So if this is y equals ln of x, that means x equals e to the y. Right, take the inverse, and if y equals x minus 2, then this would mean x equals y plus 2. And I'll just set it up here. So pi, we'll need to find our y bounds. Okay, we'll go do that in a moment using Desmos. And I don't need to shift anything because I'm just revolving around the y-axis. Okay, so now careful though, my outer function will be the line. So in this case, y plus 2. And the inner function will be the e to the y. All right, and then again, using Desmos or your graphing calculator, so -1.841 to 1.146. So let's just remember those numbers, -1.841 to 1.146. And that's your answer. Okay, and any technology is perfectly capable of finding that. That's the big ideas. There's an assignment on Canvas you can go try. It's Unit 6, Lesson 2. Please email me if you have any questions. And otherwise, thanks for watching.